Hello and welcome to the final video from week 4 of Reigate College's post-Easter work for maths. What we'll be focusing on today is proof by contradiction. Now typically this is something that students find very difficult because it's proof and therefore quite abstract. The thing is, with proof by contradiction, if you can get the first step correct, the rest of it generally falls into place, as with a lot of proof. So, how does proof by contradiction work? Effectively, what you are doing is you're saying, okay, this thing is true. That's what I'm trying to prove. Let's pretend that it's not true and show that that can't work. So, what we are going to do is our step 1 is we are going to assume the negation of the statement we are trying to prove. Now, sometimes this is directly saying this is not true, but sometimes it's a little bit more subtle than that. Step 2, we're going to use logical maths, so perform mathematical calculation or algebra, and what you'll find is that somewhere a mistake happens on purpose. That mistake is our contradiction. Because our contradiction happens, there's something wrong with our original assumption. So contradiction could be something like, 1 equals 0. We fundamentally know that that is not true. If that happens in your working for proof by contradiction, that's the contradiction. Sometimes, again, it's not as black and white as that. Sometimes it is a little more subtle. And then step 3 is conclude, as we do with all proofs. Now, the actual proof, this step 2, is generally not too tricky. Once you've done a little bit of practice, you get a feel for what they are. It's this part 1 that is quite difficult. So before we start looking at examples from the workbook, we're actually going to go through question 2 from exercise 1A on page 4 of the textbook. Because we're going to go through and have a look at the negations of each of these statements. So, part A. All rich people are happy. The temptation with this kind of thing of saying all of one thing is true is to sort of think that the negation is no rich people are happy. That's not, strictly speaking, correct. What is the smallest thing that can happen where this isn't true? So let's think about that in a different way. If all rich people are happy, what's the fewest number of rich people that we need to make this statement not true? 1. We need 1 rich person to be not happy. So the negation of this is at least 1 rich person is not happy. We're not saying none of them are, but if at least one of them isn't happy, then this statement is not true. And that's what we're looking for. So part B, there are no prime numbers between 10 million and 11 million is very, very similar. The negation to this, we're saying there are none between here. What's the smallest number of things that we can talk about to make this wrong? Is at least, sorry, there is at least one prime number between 10 million and 11 million. So part C is where we start getting a little more into the kind of thing that we're going to face in this topic. Okay, if P and Q are prime, then PQ plus 1 is prime. So the negation of this one is a little trickier. These are the things that are known. P and Q are prime. This is the thing we are trying to prove. So we can't change this statement. This is the thing that we change. So if P and Q are prime, there exists a number of the form PQ plus 1 which is not prime. So a little bit more wordy, a little bit more in depth. Let's keep going and look at D. So all numbers of the form 2n minus 1 are either prime or a multiple of 3. I'm paraphrasing slightly from the textbook, but it's close enough. So we're saying all, and we're saying either or. Obviously it can't be both, because if it's a multiple of 3, it's not prime. But either or, which means we're looking for a number that isn't one of these things. So there exists a number of the form 2 to the n minus 1, which is. So how do we express not this and not this? So the phrasing is neither nor, so it's not this or not this, is neither nor. And then part E, at least one of the above statements is true. So this is the opposite of kind of parts A and B, or specifically part B. We said, what's the opposite of at least one? Is none. So none of the above statements are true. The reason I've gone through this is absolutely the most difficult thing to do in proof by contradiction, is find the correct negation. The good thing is that this bit tends to be 1 mark that the rest of the working doesn't rely on. But if you can get it, it's still 1 mark. So let's put this into practice and have a look at page 25 of the workbook. Okay, so we're going to prove by contradiction. So it will always say by contradiction. That if n squared is a multiple of 5, then n is a multiple of 5. So first things first, we need to assume the negation. So we are trying to use the fact that n is a multiple of 5 to do some stuff with n squared. So the negation will be assume there exists some number n which is a multiple of 5 where n squared is not a multiple of 5. So that's our negation. And this is our starting point. What we are now going to prove is that this is wrong. So where's our starting point? Well, we know n is a multiple of 5 because we've written it down. That's something we assumed. N is a multiple of 5, which means it can be written as 5 times a number. So this gives us there. What are we going to do with that? Well, this is what we're looking at seeing. So let's square it. If we square it, we get 25k squared. Now we are trying to prove, or we have said, that if there is some value of n, which is a multiple of 5, that gives us n squared isn't a multiple of 5. Well, we can see that this is 25 times a number. So this is definitely 5 times a number. So n squared is a multiple of 5. Well, we said it's not, but we've proved it is. this is our contradiction, because our assumption said that this can't happen. We've proved that it must, so there's our contradiction. Okay, that is a contradiction. So therefore, if n squared is a multiple of 5, n must be a multiple of 5. Now that's generally how proof by contradiction works. There are two that you need to learn. Okay, learn by rote. And they are very, very famous proofs by contradiction. Now these ones, if you're told to work them out in the exam, may not say proof by contradiction in them. You are expected to know that they are proof by contradiction. This is the first one. Prove that root 2 is irrational. Now, bear in mind, yes, this is one you do have to learn, but they could change this number. So you will have to adapt this proof depending on what this number is, but it works exactly the same way regardless of what this number is. So this proof will work if this number's 3 or 5 or 7, whatever. The first thing to do is prove that it can be rational. Assume. The negation of this one is very straightforward because there's no ambiguity with this statement. It's just, this is true, so we're saying it's not. The thing with this is, what does a rational number mean? It means a fraction. So we have to say, therefore, root 2 can be written in the form P over Q. Okay, you can use any letters you like for this. I traditionally use P over Q. But it's more than that. Because what do we know about fractions? Well, fractions can be simplified. The point with this, and this is the really important bit about this proof, is that this fraction is in its simplest form. So where P and Q have no common factors. The other word you can use to describe this, if you didn't want to write have no common factors, you can say P and Q are co-prime, which means the same thing. The reason this is very important is this is where the contradiction happens. So we're saying root 2 is equal to P over Q. We don't like square roots, so how do we get rid of it? Well, we can square it. And we don't like fractions, so let's rearrange it. Okay, great. Well, where do we go from there? Well, it's not obvious. So let's look at what we've got and how can we describe numbers. So Q, or Q squared, can be anything. It's Q squared. P squared is 2 times a number, which means P squared is even. because it is definitely 2 times a number. Regardless of what q squared is definitely an integer because this is an integer, or these are integers. This is definitely true. This tells us that p is even. Because if a number is even and a square number, p is then also even. Okay? All the square numbers you know, all the even square numbers you know, it's always, the square root is always an even number. Now, because p is even, we can write p as 2 times something. Okay, because it's an even number, which means that p squared is going to be 4 times that number squared. Or, sorry, 2, it's going to be this squared, so 4n squared. Well, we know what p squared is. We've got that there, because p squared is up here. We said it's equal to 2q squared. So this has to be true. Let's simplify this slightly. So q squared is 2n squared. So what type of number is q squared? It's an even number, which means q is even. P and q are both even, which means they share a common factor, 2. This is a contradiction. So therefore, root 2 is irrational. Because it can't be rational. This is quite a long proof, I'm aware, but in the exam, this is 6 marks. If you can learn this and adapt it, so let's say, what I mean by adapting, let's say we had root 3 instead of root 2. Well, we'd have 3 equals p squared over q squared, and it would work the same way. Then you'd have p squared is a multiple of 3. So therefore p is a multiple of 3, and you do it the same way. So if this number here isn't 2, you just replace all of these things with is a multiple of whatever the number is. And that's the first of the 2 proofs that you have to learn. This is the easier one to remember because it's got this nice algebraic flow. The second, actually one of my favourite proofs. But it is hard to remember. And we need to prove that there are infinitely many prime numbers. Now, just convince yourself of that for a minute. The thing with proof by contradiction is they're never going to say, give you a proof by contradiction that doesn't work. Okay, this is true. Which kind of makes sense. There's an infinite number of numbers. Numbers just keep going on forever. You can prove that. Prove that there are infinitely many numbers. Well, assume that there is a biggest number. Let's add 1 to it. Oh, we've got a bigger number, so it doesn't work. Same thing with primes. There are infinitely many prime numbers. Because numbers just keep getting bigger and bigger, prime numbers do as well. But the proof is a little bit more subtle. The first thing is we need to assume the negation. So assume there are a finite number of prime numbers. Okay, so we're saying that there are infinitely many. We assume that there is a limited number. We can have a biggest prime number. Now, because we have a finite number of them, that means we can list them. So therefore, we can list the prime numbers. Now, obviously, we know the first prime number is 2, and the second one is 3, and then 5, and so on. But let's keep this nice and general. Let's call them P1 to Pn. They're just all of the prime numbers. Now, prime numbers are all about factors and multiples. The key thing about prime numbers is that every single number can be written as a product of prime factors. You take any number in the world, any integer that exists, and you are able to write that as a product of prime numbers. Take 42, for instance. 42 is 6 times 7. As a product of prime numbers, it's 2 times 3 times 7. 41 is just 41. It's prime. So one of two things can any integer in the world that exists, which is infinite, two things can happen. Either it is prime, or it can be written as a product of prime numbers. Product of prime number, both of those things mean that you take a prime number and you can put it into, or you can divide the number we're talking about by a prime number and get 0 as a remainder. Which is why we do the next step. We are going to consider a number. I call it n, but you can call it whatever you like. We are going to consider a number n that is P1 times P2 times P3 all the way up to times Pn. So we're going to take all of the prime numbers in our list and times them all together. Then we're going to add 1 to it. The reason we add 1 to it is this is where our contradiction is going to come from. We've taken all of the numbers, all of the prime numbers, and times them together and added 1. So this is a number. This is an integer because prime numbers are integers and we've added 1 to it. So this is definitely an integer. Because this is an integer, it must be written as a product of its prime factors. How do we find its prime factors? Well, dividing by prime numbers. So if you take 42, for instance, to find the product of prime numbers, you do your number tree. So let's just kind of look at that and go, okay, let's look at this as a product of prime numbers. Well, we know 7 is a prime number that goes into 42. 42 divided by 7 is 6. We know that 3 is a prime number that goes into 6. 6 divided by 3 is 2. So this is prime factorization. So what we can do, because we don't know the prime factors of n, we'll go, okay, cool, we'll divide n by P1. Okay, we get a remainder 1 because P1 goes into this bit nicely, and then we've got 1 left over. Okay, so P1 isn't a prime factor. Let's look at P2. So P2 goes into n, Okay, so let's divide n by p2. Okay, so we get p1 times p3 times p4 times all the way up to times pn. And then we get plus 1 over p2. Okay, so p2 doesn't work. And in fact, if we divide n by any number in our list, so if we take any number in this list and do n divided by that number, we definitely get a remainder 1. Which means one of two things. Either n is a prime number, not in our list, or n has a prime factor, not in our list. Because of this idea of prime factorization, n has to be able to be written like we wrote 42. Because it's an integer, and every integer works that way. So if it can't be divided by any of these prime numbers to give us a whole number, then either it's a prime number, or there's some number that we didn't write down that gives us no remainder when we divide. Both of these statements contradict the fact that we had a list of prime numbers. This list was complete, but we've proved it's not. This is a contradiction. So therefore, there are infinitely many prime numbers. This is a conceptually very confusing proof. I understand that. But it is absolutely something that if you can replicate, not with the bit I've written in pink, but replicate this, should it come up in the exam, you'll get a ton of marks. Now, proof by contradiction, I'm going to get you to do a little bit of practice, looking at exercise 1A, which is on page 4, question 3, 7, 9, and 10. Take your time with this. It is confusing. But if you can get your head around it, this is a very, very powerful method of proof. Thank you for watching.